Okay, so yeah, this is as you were just saying, this is based off work which I first presented at the Geneva conference, um, and has now been written up for publication. So this is a study that I led in conjunction with my line manager, my boss, Paul Williams, no relation, and some colleagues in Italy. Um, some of you may be familiar with Paul's work on aircraft clear air turbulence. He's quite well known in the field and in the media in general for that kind of thing. Um, I will not be discussing that at all, and I will probably not be able to answer any questions you have on turbulence. So let's get going. So as a motivation, so I'm just going to start a timer on my phone just so I don't. So motivation, as one example from 6, 7 years ago now, there was a major heatwave event in the southern UK, which caused particular disruption at London City Airport, which I don't know if any of you have been to London City Airport, but it's very small. It's a very short runway, and has lots of issues regarding this kind of takeoff performance issue. And as motivated by that event and by many other things as well, there is a European Union joint funded project called Aeroplane, which is the most hideous acronym you've ever seen in your life. Pretty much none of the letters of aeroplane actually start any of the words in the acronym. But anyway, so there's 3 or 4 main aspects of this project. One is to quantify impact of contrails, and then I'm looking at this point 2 here, identify most relevant climate metrics, so to do with takeoff performance, and then there's other aspects regarding innovative services and greener, resilient aviation. And in terms of takeoff performance, what I'm studying in the project I'm working on at the moment are 3 things. There's takeoff distance required for aircraft based on atmospheric conditions and altitude and so forth. There's a broadly equivalent metric, which is the maximum takeoff mass. And then I'm also looking at noise pollution. However, in this talk, I won't be talking about noise pollution at all. So if you're interested in that kind of thing, then we can talk offline perhaps. So the takeoff distance calculation that I have been working on is based off a slightly more simplified calculation, which you can find in a paper by Guy Grattan et al. From 5 years ago. In the appendices, there's a good description of that model. This is a model which is written in Python using Jupyter notebooks, which are portable code bases which can be shared between multiple users. It uses an open access aircraft performance database called OpenAP, which is very nice. I'd recommend you take a look if you're interested in that kind of thing. And most of the plots I've done are in the open source library Seaborn and are looking at the performance of a Airbus A320. So all of the results in this presentation are for the Airbus A320. However, the methods and the algorithms would be essentially completely unchanged for turboprop aircraft or smaller jets or larger jets. You just have to change the input parameters. We are using 30 study sites in Europe. These are made up of the 25 busiest airports. So, you've got big ones like Heathrow, Gatwick, Charles de Gaulle in Paris and so forth. And then there's 5 other airports to make up 30 in total. And the 5 kind of other airports are mostly Mediterranean tourism-based airports, which have already experienced climate change-related impacts on takeoff performance of aircraft. I'll come back to this a bit later. This is just, don't need to take any of these numbers in really, but what I've got here is a plot of the symbols in this figure for the 30 airports considered. This is the runway lengths, and as you can see, there's an enormous range from just over 1.5 kilometers to well over 4 kilometers for some of the airports. And so what for the A320 specifically, I'll come back to this later, that for many of these airports, even under extreme climate change in a apocalyptic future, the A320 would still be able to take off at these airports. I think the longest runway Heathrow is over 4 kilometers, for example. But for many other airports that are already experiencing climate change impacts, these will only be tending to get worse. And this is also true for many, many other airports in Europe, which are not explicitly considered in this study. We use inputs from 10 state-of-the-art climate models, all data for which is publicly and freely available online. I won't go into detail about the specifics of the models, but the 10 models that are used, they span a large range of so-called climate sensitivity, which is essentially the amount of warming that a particular model will predict for a given amount of greenhouse gas increase. And so using 30 study sites and 10 different climate models enables us to get a nice handle on the uncertainties involved in the data I'm going to be showing you. So the data that we're looking at are made up of daily data from 30-year periods. So obviously that's a lot of different days. Just some example plots here of, for example, the temperature data, the surface air pressure, and obviously you can see this, the 30-year seasonal cycle in this data. But just going forward in this presentation, I'll only be showing Northern Hemisphere summer. I'm trying to get used to that again with JJA being summer rather than winter. So yeah, these are all JJA, and the time periods used, we compare a 30-year historical period, which is from 1985 to 2015, and then a future 30-year period, which goes from 2035 up to 2060. So what I've got here in the first of our kind of results plots, these are distributions of the takeoff distance required for, this is for one particular model and one particular airport, just to illustrate the type of data that we can get. So these are so-called box and whisker plots, which illustrate median, interquartile range, and outliers in the distribution. So well, actually, see if I can get a pointer. I think I can. Laser. So basically, the outliers down here represent unusually cold days. The points up here represent unusually warm days. And so if we plug in our temperature and pressure data into the model, then for the historical and then for 3 future climate scenarios, shows that what we predict is a steady increase in the takeoff distance required. I should just say, I should have said this earlier probably, that for the future scenarios, obviously we don't know exactly what's going to be happening in the future, and so what we've used for the 3 future scenarios is essentially a kind of optimistic, middle of the road, and pessimistic future scenarios. So I should have said that earlier. But basically, the headline of this figure here is that for this particular airport and this particular model, which is representative of the model ensemble as a whole, is that the mean values are set to increase by approximately 50 meters by mid-century compared to the end of the 20th century. There is very significant uncertainty in these numbers, of course, which is based off the fact that not all days are the same warmth. But broadly speaking, warmer days means lower air density, which means you need a longer distance to take off for given thrust parameters. Can't seem to go on to the next slide. Okay, here we go. So next slide here shows distributions of the takeoff distance required on the right-hand side, and on the left-hand side shows distributions of daily maximum temperatures. And the bottom blue figures here are for the historical data, and then optimistic, middle of the road, and pessimistic futures. And broadly speaking, there's two main things to note here. The first one being that, as is clear, and as I'm sure we all know, that with climate change, the average temperature of a distribution will increase. This is our global first order global warming effect, but something which is quite unexpected from a kind of thermodynamic point of view. If you're just looking at kind of static atmospheres and ideal gases, is that you actually get a significant change to the distribution of temperatures, daily temperatures across these periods, and so essentially what we're saying here is that although the historical set of temperatures looks broadly like a bell curve, but as you go to hotter and hotter temperatures, the distribution of warm days, you get many more warm days, which means you get a lot more days where you need a lot more runway to take off. That's the headlines. Now air pressure varies as well, obviously, and we're just using a simple first order ideal gas law in this calculations. And since the air pressure is changing as well, that also affects the density of the air, which affects the takeoff. And so, for example, this is just a kind of a bit of an aside, is that for again, for the same model and the same airport, if you take the days which are all at a daily maximum of 20 degrees, the air pressure can vary significantly, and that can have an effect of up to 50 meters on the takeoff distribution, just purely from a change in air pressure for the same temperature. So although we all tend to think about temperature as a primary variable because it's something we all obviously experience every day, it's the air pressure is not something which is quite so intuitive to many people, myself included. But that's just an aside. Now, don't worry about this crazy chessboard of data here, because I'm going to be zooming in to the bottom left here. So I'll just talk you through this. So what I've got here is I've just zoomed in on these bottom four left airports, and so the four letter codes here are the ICAO codes for four different airports, and these are again all for JJA. And so what we've got here is for the SSPs 1, 3, and 5, so our optimistic, middle of the road, and pessimistic futures. These are the probabilities across the model ensemble of the future periods exceeding the 99th percentile of historical takeoff distance. And so what that means in kind of normal language is that in our historical period, if we look at the amount of runway required, the maximum of that, which is only one day out of 100, so 1% of the time, this shows that in the future we might be expecting for extreme climate change cases that we might be expecting these exceptional historical events to be occurring up to half the time. And so this obviously has significant potential impacts on runway maintenance procedures and weight restrictions, which I will talk about in a second. Okay, so basically, for the takeoff distance required values that I showed earlier are all predicated on assuming that the A320 in our model is maximally laden, is full, is I think 78 tons, I think is the metric tons, I think is the number. However, for I showed earlier a scatter plot of runway lengths. Several of these airports, and I've just got four here. Chios in Greece, Pantelleria in Italy, San Sebastian in Spain, and Rome, Campino in Italy again. The runways at these airports are so short that a maximally laden A320 can never take off from them ever, even in the absence of climate change, just because the runways are not long enough. And so what we've done here is look at, for future climate change scenarios, how many fewer passengers for an average flight will an A320 be able to take off with from these airports. And so I've got my magnifying glass here. I'm going to zoom in the next one, just so you can see these better. So this is for Chios Airport in Greece, and for our optimistic future here, our SSP1, this is a pretty static value as we go from 2035 to 2060. But even for an optimistic future, we're projecting a reduction in the number of passengers that can be carried on an A320 of about 5 or 6 passengers. And just to emphasize, that is on every single flight taking off from those airports. This isn't like some kind of seasonal, average or an outlier. This is saying that we project that there will be that many fewer passengers on every single flight, assuming a one-off comparison to the historical data. And then if we look at our pessimistic future, where the greenhouse gases essentially increase without limit, you get a steady increase in the number of people who would be kicked off the plane, like the British Airways flight at the beginning of this presentation. And so worst case scenario, you're looking at more than 10 people fewer on each A320 from this particular airport. I won't go into this too much. I'm more than willing to talk about this offline to anyone. But what I've just shown in the previous slide is essentially the kind of central estimate. But if I look at the probability distribution of individual days maximum takeoff values compared to the historical, we see some pretty stark values. Again, we see the change in distribution shape from a broadly kind of unimodal Gaussian bell curve to a significant increase in hot days, affecting the number of passengers that can be carried, or passenger equivalent weight. All of this could, of course, be achieved by reducing payload in other ways. But extreme values of passenger equivalent weight reductions could potentially exceed, on average, up to, it's in extreme cases, up to 20 passengers per flight by 2065. This was a nice little surprise. The paper where every single figure that you've seen today is taken from has been published in an open access paper, which was published today, which was quite nice. Wasn't planned that way, but it was obviously meant to be. So in conclusion, we've used the takeoff performance model to calculate summer takeoff distance required for an A320. We've used 30 European airports and 3 future emission scenarios, as well as 10 state-of-the-art models. So due to climate change, magnitude and distribution, and it's the and, which I think is really crucial here, the distribution of takeoff distance required is projected to change significantly, even for comparatively small future warming. And although the variability is large, extreme values for takeoff distance may be up to 100 meters larger in the fairly near future. Climatic conditions necessitating extreme runway utilization are expected to occur as much as half the time in the future. So this is what I was saying earlier about a 1 in 100 day event becoming potentially as often as 1 every 2 days. And although many airports have runways which are more than long enough to cope with this, at least 4 of our study sites may have to reduce payloads by as much as 10 passengers per flight by 2065 compared to historical values. So just like to acknowledge the funders, my collaborators, many helpful discussions with people from all over, and you all for your attention and the invitation to speak. Thank you very much.